For the rocket architecture, we have the rocket divided into sections. The nose cone, where a non-deployable 3-unit CubeSat payload is stored. The upper airframe for the drop and main parachute. The upper airframe for the avionics plane. And the upper airframe lower section for the main venting valve. Middle airframe is for the oxidizer tank, and lower airframe for the main oxidizer valve, while lower airframe stores combustion chamber, fins, and bolt payload. This rocket has hybrid propulsion and a dry mass weight of 25 kilograms with a total length of 3 meters. Total weight, including propellant and motor, is of 32 kilograms. The general concept of operations of the vehicle consists of the takeoff, the boost, and the main engine cutoff at 700 meters. Then the predicted apogee will be at 3,100 meters, with a drop chute deployment at 2,800 meters. Finally, the main chute deployment will occur at 700 meters until touchdown.
Our hybrid rocket engine will use nitrous oxide as the oxidizer and paraffin wax as the main fuel. It will work at a maximum pressure of the tank of 6 megapascals and 2 megapascals at the combustion chamber. It will require 5 actuators in order to operate this engine. We develop a software that can deliver simulations of the thrust curve, predicting the pressure of the chamber and the oxidizer tank and the burn rate of the paraffin wax. With this, we calculate the ullage and select various sizings of the engine. Also, we are in process of static fire tests.
Nose cone geometry is defined by the power series 0.5 with a fitness ratio of 4.5 to 1. This nose is made of carbon fiber body with a forged carbon fiber tip. It has a 3 CubeSat units payload capacity. Our airframes are made of carbon fiber or fiberglass, and couplings are manufactured with aluminum. For this rocket, we have a 4-fin arrangement with a modified rhomboid geometry. It is made by various carbon faces with different orientations, making a sandwich layout. It has an aluminum core and fiberglass in between to avoid corrosion. We will use an epoxy filler.
This system is composed of 2 stages: the drop parachute deployment at apogee and the main parachute deployment at 500 meters above ground level, using a carbon dioxide mechanism and a tender descender respectively. For the drop parachute, it will use a commercial balloon canopy, which will provide a 26.18 meters per second final velocity. In the case of the main parachute, the design is based on the flat standard skip canopy, which will provide an 8 meters per second final velocity. Before the apogee, the main parachute and the drop parachute are contained on the recovery bay. After reaching the apogee, the COT mechanism pressurizes the recovery bay, deploying the drop parachute while the main parachute is restricted by the tender descender. After hitting the 500 meters over ground level, the tender descender is activated, deploying the main parachute.
Recovery electronics rely on 2 COS computers for redundancy. The COS computer is the Rocket Recovery Controller 3 of MissileWorks. It comes with a barometric sensor and 2-stage recovery deployment of drag chute and main chute. Inside our avionics bay, we carry a GPS tracker for helping recovery labors, and also a SRAD computer fully designed and developed by us, including barometers, magnetometers, and inertial measurement units. It also comes with instrumentation for monitoring in real time our hybrid motor. For us, it is critical to know variables such as pressure inside the tanks, temperature, and other variables. Our system is designed so this data can be transmitted in real time to us by a Moxon antenna mounted on the avionics bay. As mentioned before, our SRAD computer is in charge of acquiring all significant data before, during, and after the flight. It will not be in charge of recovery at all, only data acquisition and telemetry. We conducted a series of tests on our radio frequency circuits and antennas for ensuring a reliable telemetry system. Lastly, our payload consists of a 3-unit CubeSat carrying several experiments that pretend to measure how blood consistency changes during spaceflight. This with the purpose for ensuring safe transportation of blood in the near future.